So today we have Carissa speaking on slice towers of trivial suspensions of HF2 over C2.
All right, well, thank you all for having me. I'm excited to be here virtually. So today, I'm going to be telling you about the slice filtration. This talk is not so much a theory/results talk as I want you to walk away knowing how to calculate some things for the slice filtrations and having a feel for how it works. So slice filtration, a little setup first. Oh no, didn't I? That's not good. We're already having technical difficulties. There we go. Okay, so the slice filtration was developed in the early 2000s by Hill, Hawkins, and Ravenel. And their solution to the Kerber invariant one problem. Essentially, what the slice filtration does is that it decomposes genuine G spectra into these things called slices. And the way I like to think about them is that they are irreducible pieces. So the goal with the slice filtration is to take a genuine G spectrum and break it up into these irreducible pieces, along with the tower, which tells you how to reassemble the pieces into your original spectrum. Right now, the literature is mostly focused on trivial suspensions of Eilenberg-MacLane spectra, and I'll explain this notation later on in the talk. We have some complete characterizations. So we know what 1 slices are. We know 0 slices. And we know -1 slices. So we have a complete characterization for any sort, you know, exactly when a spectrum is one of these 3 things. But beyond the work of Hill, Hawkins, and Ravenel on mu and c to the n, Hill and Yarnall on cp to the n, where p is odd, and Guillou Yarnall on line 4, or C2 times C2. Not much is known. The slice filtration is generally mysterious. For example, it doesn't even commute with trivial suspensions. So normally when you have some sort of filtration, they'll commute with suspensions, but in this case, it doesn't. And most of the focus so far is when your suspension is at least 0. All right, so it's the general idea right there. First, we have some necessary background that I need to set up before I even tell you what the slice filtration is. I promise there will be definitions. So first of all, we need to know what representations are. So sigma is the one-dimensional sign representation of c2 to the n. What that is, you have r and an x by flipping. if you take, and this is the 1-point compactification, S sigma is, we call that S sigma. Now, when we have CW complexes, we keep track of, we write down the cell structure. S sigma has a group action, though, an action by D2. So we actually have an equivariant cell structure. So here's what it looks like. When we compactify, 0 and infinity correspond to two fixed C2 on C2 0 cells, because they're not fixed by the action sigma. And then we have the two intervals, negative infinity to 0 and then 0 to infinity. And those correspond to a single free C2 mod E one cell. So now with representations and representation spheres, we're not only keeping track of cells by dimension, we're keeping track of them by orbit as well. So if we were to think about the underlying cell structure of S sigma, well, then you have 2 0 cells and 2 1 cells. So when we think about the group action of the orbits, it becomes a single 1 cell because the 2 1 cells form an orbit. An important representation here to know is the regular representation. And that's always usually denoted by rho. And it's 1 plus sigma, where 1 is the trivial representation. So it's just R with no action, or rather the trivial action. All right, so along the genuine G spectra that I think about all come from representation spheres. And what a genuine G spectrum is, essentially, is a spectrum with a group action built into its bones. That's how I like to think about it. It's an equivariant spectrum, but we construct it with the group action just like very much built in. For example, S sigma, we keep track of the cells by orbits. So when we take the suspension spectrum with S sigma, that's a genuine G spectrum. Now, when we move into this realm of genuine G spectra, the homotopy stops being just a Mendelian group. Because now we're keeping track of all of this information by orbits. So then our homotopy is going to have information for each orbit. And what that homotopy is called is a Mackey functor. So Mackey functor M. And this is for a finite group G. It consists of abelian groups for each orbit. And every time you have a subgroup containment, you're going to get maps. So we'll have an M of G mod H and M of G mod K. Going down, we'll have what are called restriction maps. And going up, we have transfers. And then at each level, we have a Weyl group action. And these maps satisfy the double coset formula. Pictorially, they're usually represented using like Lewis diagrams, which I will give you an example in a moment. Right, so we're going to set G to be C2. And then the only Mackey functors for today are going to be little f, capital F, and little g. So we write the orbits from biggest to smallest to biggest going down. And in each spot we need a group. So little f is going to be a 0 and an f. So little f is for free because we have a single non-trivial group at the free orbit. Capital F is called the constant Mackey functor f. And so the restrictions are always going to be identities. The transfers are the index of this group and this group. But that here that's 2. F is the finite field F2. I don't usually write the 2, but that's what that is there. But you know, in the finite field of 2 elements, 2 is 0. So we just have the one out there. And then G is a geometric, we'll just have an F at the top. So these are the only Mackey functors you need to know for today. One awesome thing you can do with Mackey functors is that you can have short exact sequences. So those happen level-wise, and all of the squares commute, which here it's kind of trivial. Now earlier I wrote this H underline M. Oh, and a Mackey functor was always denoted by the letter with a line underneath it. So I wrote this H underline M. That is an Eilenberg-MacLane spectrum. With a single homotopy Mackey functor. Pi 0 is M. So it's same idea as non-equivariant Eilenberg-MacLane spectra, except now our homotopy is the functor. So for example, we have H little f, H capital F, and HG. And aside from suspensions of these spectra, these are the only spectra we're going to talk about today. Now, we have some pretty great things we can do with short exact sequences of Mackey functors. This short exact sequence, when you turn each of these Mackey functors into an Eilenberg-MacLane spectrum, well, you get a cofiber sequence. Which is super awesome for calculations because we're decomposing genuine G spectra. And one thing that's helpful for doing that is to have, well, we need cofiber sequences. We'll see why later on. And a great way to get cofiber sequences is to go to Mackey functors, because it's a lot easier to write down a short exact sequence of Mackey functors than to figure out a cofiber sequence. All right, so there's a couple things I'm going to ask you to take for granted, and if you want to know why they're true, I would be more than happy to tell you or walk through the calculations at the end of the talk, but I want to make sure we actually talk about these sliced towers. So just believe me, for now, just believe me when I say that when you take the row suspension of H little f, that is actually homotopic to the second suspension of H capital F. And when you take the sigma suspension of H little g, well, you just get Hg back again. So Hg is invariant under the action suspension by sigma. All right, and these are all of the tools besides like the slice filtration definitions, etc. That's all of the background we need for today. So now we can actually say what the slice filtration is. Definition. For each integer n, we're going to let tau at least n be the localizing subcategory of genuine G spectra of a particular form we take the suspension spectrum of G mod H plus smash SK rho H, where H is a subgroup of G. Rho sub H is the regular representation of H. And K times the order of H needs to be at least 10. And so we're going to call or say that X is at least n if X is in tau at least n. All right, so what we're doing here is that we're taking a representation sphere for K, meaning for H, and inducing it up to be a representation sphere for G, and then we're turning it into a genuine G spectrum by taking the suspension spectrum. Now, we have this localizing subcategory.
Can I ask a historical question here?
Yeah.
If I remember correctly, Hill-Hopkins-Ravenel uses a different definition of slice filtration.
Sorry, could you repeat the question? I couldn't quite hear.
Yes, sorry. If I remember correctly, Hill-Hopkins-Ravenel uses a slightly different definition of slice filtration.
Yes, great question. So Hill-Hopkins and Ravenel came up with slice filtration, and then later John Ullman modified it to get the regular slice filtration. And the only difference is a shift by 1 in the dimensions.
Yeah, exactly.
So everything I'm doing today is using the regular slice filtration.
Okay, thanks.
All right. So we have this localizing subcategory, and for us that means a lot of things. So first of all, it means that we have a full subcategory, which is closed under weak equivalences. It is closed under cofibers. It's closed under extensions. It's closed under retracts and infinite wedges. And finally, it's also closed under directed colimits. So this is a lot to ask. But the reason we ask for that is that it's great for calculations. So most of the things that I would want to do, I can do because I have these properties. Another thing that a localizing subcategory also gets us is that we have a localization functor. P star. And what that does is that it takes us from genuine G spectra and dumps us into the tau at least n. And along with this comes natural maps from P upper n plus 1 of x to Pn of x, where x is a spectrum. We have fiber sequences, P lower n plus 1 of x to x, P upper n of x. And I'll say what the P lower n plus 1 is in a moment. And then we also get a tower. So I'm going to have P2, 2 of x to P upper 2 of x. And P upper 2 of x maps to P1 of x. And then we have P0 of x. And each of these little pieces are fiber sequences. So we have the map from, say, P2 to P1. We take the fiber of that, we call it the upper 2, lower 2. The way to think about this is that we're building x through its homotopy. The upper 0 of x is going to have homotopy of x at least 0 and above. P upper 1, homotopy at least 1 and above. P upper 2, homotopy at least 2 and above. So here, this is a ceiling. Yeah. And here, well, the lower means nothing above. So P lower 2, we don't want anything above dimension 2. All right, now by definition, P upper n of x is at least n. And then P lower n plus 1 of x is less than or equal to and less than or equal to n. It's a bit of a weird definition. So a spectrum x is less than or equal to n if for all h contained in your group G and k such that k times the order of h is at least strictly bigger than n. We have for all r at least 0, s k rho h plus r mapping to x. We want the h equivariance maps to 0. And what that means is that there are no generators, no maps from generators. Of tau at least n plus 1. And here, one thing to keep in mind, or just to note, is that if x is an n slice, so one of those these fibers are the n slices, or the irreducible pieces that we want to find. So if x is an n slice, i.e. it's equal to a fiber, then x is both at least n and no bigger than n. And so these are the irreducibles that I mentioned earlier. So when we're looking for slices, or these irreducible pieces, we're looking for spectra that are equal to n. All right, now that we have our definitions, we have some very helpful theorems for calculating things. All right, and this is due to Hill, Hopkins, and Ravenel. So if we're going to take any spectrum X, any number n or integer n, and any integer k, the upper n times with plus k times the order of g. So the fiber or slice of that dimension of the k row suspension of x is homotopic to the k row suspension of the upper n, lower n of x, which just means that the slice filtration commutes with suspension by the regular representation. So for example, if we take G to be C2, well then the row suspension of the zero slice of a spectrum X, well that's going to be P0 plus 2, 0 plus 2 of the row suspension of X. And this 2 is because the dimension of row is 2, because both 1 and sigma are one-dimensional representations. So whenever you suspend by row, you can either throw it into your slice or pull it back out of the slice, which is very useful for figuring out towers. All right, another helpful theorem. And I mentioned this earlier, we know what the 1, 0, and -1 slices are. I'm going to tell you what they are. So this first one is due to Hill, Hopkins, and Ravenel. So if we take an Eilenberg-MacLane spectrum, it is a one, if we take the one suspension of it, it is a one slice if and only if all restrictions in M, our Mackey functor, are injective. The second thing we know, also due to Hill, Hopkins, and Ravenel, if we have an Eilenberg-MacLane spectrum HM, it's a zero slice for every single Mackey functor M. So pick whatever Mackey functor you want, take the Eilenberg-MacLane spectrum of it, it is a zero slice. And finally, this is due to Ullmann. If we desuspend our Eilenberg-MacLane spectrum, it's a -1 slice if and only if all transfers to the maps going up in M are surjective. So one thing to note about this last point is that Ullmann actually writes down the entire tower for the desuspension of the Eilenberg-MacLane spectrum. For any M, where again, M is an Mackey functor. But beyond this, no one really knows, or no one's really really thought about the suspensions of Eilenberg-MacLean spectra. And that's what I'm actually looking at with my work. So I've focused almost completely on desuspensions of Eilenberg-MacLean spectra. And what we're going to do today is write down the complete tower for desuspensions of the constant Mackey functor F over C2, rather HF.
Can I briefly ask about Willman results?
Pardon?
Yeah, can I briefly ask about Willman result?
Willman result? Yes. Okay.
Yeah. So, what is the pieces in this tower? It's again Eilenberg-MacLean spectra, or it's something more sophisticated?
So he only writes it down for the Eilenberg-MacLean.
No. I understand what you wrote down for this one, but I'm asking what are the pieces in this tower? What are the stages?
A desuspension?
What is the slices in this tower? What is the pi n n? It is always a Eilenberg-MacLean spectra or something more sophisticated.
So slices usually take the form of some suspension. Let's write that with a better color. Of an Eilenberg-MacLean spectrum, because really people mostly focus on are the Eilenberg-MacLean spectra, because we don't really understand the slice filtration in general, so we take the most basic genuine G spectra we have and then play around with it. And V is a representation of your group.
So you're saying what?
So here, where I have the -1, that is a virtual representation. So the desuspension of HM is S-1 smash HM.
Yes, thank you. But I ask you a different question.
Oh, sorry.
So you take a desuspension of a Eilenberg-MacLean spectrum associated to some Mackey functor, and you write down a tower for it.
Yes.
This tower. So I'm asking how the pieces in this tower looks like.
Oh, I'm about to show you.
Okay. But this will be again some Eilenberg-MacLean spectrum or not?
We will get suspensions of Eilenberg-MacLean spectra, but not all of them will be trivial suspensions.
Okay, thank you.
All right, so as was just foreshadowed, we're going to write down the towers. So we have some calculations. Before we start writing things down, I have a couple slogans for you. If it looks like a slice, it is a slice. And if it looks like the tower, it is the tower. All right, now let's take a quick recap of our nice tools. So let me remind you what our Mackey functors were. So we have the free Mackey functor with a 0 and an F. We had the constant Mackey functor F with an F in each spot. And then we had the geometric Mackey functor. And of course, we had a short exact sequence of these Mackey functors. All right. And then there were these equivalences that I asked you to just believe me on. So the row suspension of HF, little f, is homotopic to the second suspension of H capital F, which gives you that the negative n suspension of H little f, or any n, is homotopic to the negative rho plus 2 minus n suspension of H capital F. And that will be very useful for us in a moment. And then HG was invariant under suspension by sigma, which means that you take the row suspension of HG, well, you're just going to get the one suspension of HG. But row suspensions give you slices. So this is a 2 slice because the dimension of row is 2. Therefore, for any integer, any integer k, the k suspension of HG is a 2k slice. And reminder, all of this we're writing down today is for C2. Now, we can take those couple pieces of information and take our Eilenberg-MacLane spectra, HF to HF, HG, and then we can use our nice little equivalence here to get a fiber sequence or co-fiber sequence where we get rid of the little f. I'm going to call this equation star. Just a note, S negative sigma is just the dual of S sigma. All right, let's start calculating a couple of things. What happens when n is 1? Well, we're going to get a negative rho plus 1 suspension of HF to the negative 1 suspension of HF to negative 1 suspension of HG. All right. This is a negative 2 slice. This is a negative 1 slice. Now why? Well, one suspension of an Eilenberg-MacLane spectrum is a 1 slice if and only if the restrictions are injective. The restrictions are injective here. And then when you suspend by negative rho, well, then you're just subtracting 2 from that slice. So that's 1 minus 2. All right, our tower has to start with a slice and end with a slice. So we have our co-fiber sequence. It starts with a slice, it ends with a slice. This is the tower. Again, the slogan, if it looks like the tower, it is the tower. If we move on to n equal to 2, well, now we're going to get the negative rho suspension of HF to the negative 2 suspension of HF, the negative 2 suspension of HG. All right. Well, we have a negative 4 slice now. Here, well, Eilenberg-MacLane spectra, 0, they are 0 slice. Co-fiber sequence, it starts with a slice, it ends with a slice, therefore it's the whole tower. When we move on to n equal to 3, however, things get a little bit more complicated. So I'm going to write it slightly differently. Negative rho minus 1 of HF. So this negative 3 suspension of HG. That's our negative 6 slice. I'll write it as P upper and lower negative 6. But because we have a co-fiber sequence, a non-trivial tower, for the negative 1 suspension of HF, it's not a slice. Therefore, when we desuspend by rho, it's still not a slice, because rho preserves slice status. So now we've run into trouble because we have a partial tower, but it needs to end, or rather start with a co-fiber sequence. But doesn't that look familiar? We can use this because desuspending by row maintains slice status. So actually, should not have written there. We're just going to desuspend this whole tower by negative row. So then we'll get a -2 row suspension plus 1 of HF and a -2 suspension of HG. So that will be our -4 slice, and this will be a -3 slice. So now we have strong co-fiber sequences together. It starts with a slice, and then all of these end pieces are slices, so we have the entire tower. When we move on to n equals 4, it's the same thing. And I'll show you n equal to 5. Spoiler, it's basically the same deal. We'll start down here with the -5 suspension. Negative row -3. Now remember, the -3 suspension, not a slice because it has a non-trivial tower. So we're going to play the same game as earlier, where we take this whole thing and we desuspend by row. So then we'll get a -4 suspension of HG. That's our -10 slice. That's our -8. The -2 row -1 suspension of HF and a -3 suspension of HG. And finally, a -3 row +1 suspension of HF, which is our -5 slice. And so on and so forth. You just keep doing this. So if you write it up all nice and fancy, and formal, proposition for G equal to C2, the slice tower for -n suspension of HF, where n is equal to 2m plus r, at least 1, and r is either 0 or 1, is, well, at the top we're going to have -m row plus r HF, which is our -n slice. Then we're going to move on down to the -n-1 row plus r-2. Now we start tacking on a bunch of these HGs. And we keep peeling off copies of row all the way until we get to the -n suspension of HF. And that is the whole tower for the -n suspension of HF over C2. There's a lot of ways to write the tower. For example, we could have stuck with the little f, but I like to use f's all the way down, because then you can see how the -n suspension morphs and changes, and how many copies of row you gotta throw in there in order to get a slice. So you can see how quickly it becomes a slice or how far away it is from it. All right, and that's all I have for you today. hopefully feel comfortable with calculating some towers for C2. Basically, what you want to do is get your short exact sequences of macupunctures, turn them into co-fiber sequences, maybe muck around with a few homotopy equivalences, and then you just start putting things together. And with C2, there's this nice two periodicity. So do you have any questions?
Well, first, on behalf of everyone, I'd like to thank you for the talk. But yeah, we can continue with questions.
Hey, I was just wondering, great talk, by the way. I was just wondering if, like, I think it was, can you go back to like Hill-Hawkins and Reminisce theorem?
Yes.
Thanks.
So,
like the one above that.
Okay, so the commuting with row, yeah.
Oh. Okay. Yeah, I guess then I wasn't actually thinking what I was thinking then. Maybe I'll ask you later.
Okay.
Yeah.
Can I ask a question? Can you go to where you're defining this category tau sub greater than or equal to n?
Yes.
Great. So this looks like it's coming from a T structure. Is that correct?
I'm not familiar with T structure. Could you give a definition?
Not quickly, so maybe we can talk about this later. And I was just.
Could be, I'm not familiar with the phrase.
Okay. The thing that was worrying me is that it seems sort of the maps are going in a strange direction for me. So do you have, so you said this there's a map from X to its sort of localization in here?
Mm-hmm.
Okay. Seems sort of the opposite of what I would expect from a T structure, since you get maps from connective covers down.
Yeah. So for positive integers, you are talking about sleep connected covers. The non-equivariant, one way to think about this is that you have the filtration, which is a filtration of non-equivariant spectrum. And then it literally, in each level, you have you build your spectrum by the homotopy. So you have, say, T0 of X is homotopy up to dimension 0. T over 1 up to dimension 1.
I think I was using a different grading convention than you. I think
Okay.
you have homological and cohomological mixed up. I see. Okay,
Yeah,
thank you very much.
So, so the upper lower 1 of X is going to have exactly pi 1 for X. And the slice filtration is a genuine equivariant generalization of the Postcop tower.
Could I ask you, Carissa, if you have any, if there are any sort of slice spectral sequence computations or something that you have in mind that such nice decompositions might lead to?
So you can write down the slice spectral sequence for these C2 towers. I haven't because I mostly played around with them to get a feel for the slice filtration. I think a lot of people have written down these towers on their own, but no one's really published it. What I'm focusing on now, though, is towers over climb 4, or C2 times C2. So I want to know things about negative end suspensions of Gallon break McLean spectrum HZ. So it's going to look like A-body, right case, line 4. And we've got 3 C2 subgroups and 3 orbit. Yep, that's a K up there. So you have a bunch of Z's. The restrictions are 1. And now since Z is not characteristics 2, then you're actually going to have transfers in term multiplication by 2. So what I'm thinking about, what I'd like to know is like the slice spectral sequence for this sort of thing. That's what I'm working on figuring out at the moment.
Okay, cool.
Okay, are there any other questions? Well, if not, I'd like to thank Carissa again